Welcome back to our course in stochastic processes. In this video, we will learn about the discrete stochastic integral. So that is a preliminary thing for the stochastic integral you will learn in the next lecture. It's actually a method to make new processes from other processes. In particular, we will see that the stochastic integral is a martingale if the underlying process is a martingale. So let's see what all that means. So, the discrete stochastic integral. We will first have to deal with the so-called dupe decomposition, which is the following. You have some stochastic process, x, and you want to decompose it into two things. You want to decompose it into a martingale and something else. X equals m plus a, where m is a martingale, and a is called previsible. We didn't have that yet. We only had adapted, and that's something similar. Only time is shifted by 1. So x is called previsible if xt is ft minus 1 measurable. So the best thing you can think about this maybe, let's say you have some game of chance or so, and ft is the filtration which carries all information up to time t, so up to the tth experiment of chance that you do. And before this thing occurs, so before the tth round of this game, you maybe want to bet. But when you bet in the tth round, you only have the information for the first t minus 1 rounds. So the thing that you're betting, so the amount of money you're betting, call this xt, and that is ft minus 1 measurable. That's not ft measurable. That would be too simple, because then we could just bet using the result of the tth round already. But you can only use the first t minus 1 rounds when you want to decide how much money you bet in the tth round. So in this case, xt is ft minus 1 measurable. And as we said, we want to decompose the stochastic process x into a martingale and a previsible process. We can always do this. That's what is said here. That's what it's meant here by this sentence. It's a bit short, but that's what it's meant here. And the martingale and this process A, they are unique. So that's a unique decomposition of x into m and a. And x is a submartingale if and only if this previsible process here is almost surely non-decreasing. The proof is quite simple actually, because I can just write down what the process A is, and yeah, by this I already have anything, because I can also show that's the only thing that works here. And I just write it down. That's this here. So I'm summing over all times, so over all rounds of the game of chance, for example. And I'm summing the proposed gain in x. Given I have the information up to time s minus 1, I compute the expected gain from s minus 1 to s. When I do this, I can also compute m, which is x minus a. And it's easy to see that m must be a martingale, because x is something. I subtract from x, I subtract what happened on average. And that means, well, I could compute the expectation of mt, or let's say of mt minus 1, given ft minus 1. Okay. AT as you see here. I only condition up to ft minus 1. So at is ft minus 1 measurable. Xt is not necessarily. But what I have here is, so that must be the same as the expectation of xt minus 1 given ft minus 1. So from the first term here. And for the a, I subtract two things here. I have a sum up to t. I subtract the same sum up to t minus 1. And what remains is the last summand, which is the expectation of xt minus 1 given ft minus 1. And of course, now I have the same thing, so that's 0. And that shows that M is a martingale. For uniqueness, we have, well, suppose we have a decomposition from x into m and a, and then I could compute at minus 1, and at is ft minus 1 measurable. That means that this thing here must be the same as the conditional expectation of at minus 1 given ft minus 1. But at is also x minus m. And when I plug in here x minus m, for the m bit, so when I exchange a by m here, that's 0 anyway because m is a martingale. So that must be the same as the expectation of xt minus 1 given ft minus 1. And that shows that at must be exactly of this form here, and I am done. Okay, great. Let's do something else. The so-called quadratic variation process, which will also play a big role in this lecture and also in the next lecture, in the next semester. We know that if I have a martingale, if I take a convex function of a martingale, I get a submartingale. It has to be an increasing and convex function of a martingale is a submartingale. And that means the square function is such a function which is increasing and convex. Or do I need increasing? Maybe I don't even need increasing, I only need convex. I think I only need convex, yes. I only need that x is convex in order to be a submartingale, so xt squared is a submartingale. And that means, we didn't talk about this yet. For a submartingale, I can make the decomposition of the submartingale x squared into a martingale and the previsible process. But it's clear that the previsible process must be almost truly non-decreasing because it must be of this form here. And that's a random variable which is non-negative, almost truly. And that means that the A process is almost truly non-decreasing. And when I start with a submartingale x squared, where x is a martingale, I get an almost truly non-decreasing process A here, and that process I call quadratic variation process of x. And we can compute things with this because, well, that's this x here in this funny brackets, in this angle brackets, that's the same as this at here if this x here is x squared. If the x from this slide is the x squared from this slide. And that means I can use this formula here. And I get squares here. I get squares here like this. And here is a thing which seems to be very funny and wrong at first sight, because here I have the difference of two squares, and here I have a square of two differences, and of course that's usually not the same. But in this case, this equality holds. And the reason is, and you can please recall this calculation because it comes very often. When I have this here, I can write instead, that's the expectation of xs square minus 2xs xs minus 1 plus xs minus 1 square given fs minus 1. I just multiplied the square here. Okay, this here I just leave alone because I have this also here. Here I have an xs minus 1, which is also here, but it carries a plus, and here it carries a minus, so I have to do something. And the mixed term here, I can do something with conditional expectations, because I can write, let me write it here, xs square minus, so xs square given fs minus 1 minus 2 times, and xs minus 1 is fs minus 1 measurable, which means I can put it out here, xs minus 1. I am left with the expectation of xs given fs minus 1. And of course I also have the expectation of xs minus 1 square given fs minus 1. But now x is a martingale, and this conditional expectation is xs minus 1, which is the same as this here, which means I subtract xs minus 1 square 2 times, and I add it 1 time, which means I, in effect, subtracted 1 time, and that's the reason why this equality here holds. Okay, that's for the quadratic variation process. And its expectation, I just have to write down expectations here. That's this sum here, or xs squared minus xs minus 1 square. That's a telescope sum, of course. So that's the expectation of xt squared minus x0 squared, which is, yeah, the variance of this thing here, using a similar trick as before. So usually, or very often, x0 squared is 0 anyway. So you get the variance of the increment between time 0 and time t. So that's also something you can remember. The expectation of the quadratic variation process equals the variance of the increment. Okay, let's look at some examples. So x is square integrable, so all x are square integral, and I sum them. Then, okay, and what do you have to compute in order to get the quadratic variation process of my s? And the answer is I'm doing this here. So I'm taking the martingale, which is, or I should look here. I'm subtracting the martingale at 2 time points, and I square it. When I subtract the martingale at 2 time points here, I just end up with a single x here. I square it, I take the expectation. Well, I take the conditional expectation of xs square given fs minus 1. And I forgot here, they have to be IID. No, they have to be independent, not, I didn't do this, so they have to be independent. Because then this conditional expectation vanishes and it just becomes the expectation, and I get that the quadratic variation process is this sum here. Most importantly, it's a deterministic thing. So here is no random variable, so that's just a deterministic number. which means the quadratic variation process is a deterministic process in this case. That differs if I do not take the sum of the x's, but the product, because then I can make the same calculation as before, take the difference of the s. But what's the difference of the s? That is s minus 1. So ss equals, equals s index s minus 1 times xs. When I write it like this, I can pull out the s at time s minus 1 square here. But I end up with xs minus 1 square. Given fs minus 1, but if they are again independent, I forgot this, that's important, if that's independent here, I can forget about the conditional expectation, and I get this here. And here, of course, the process s at time s minus 1, that's a random variable, that's not deterministic usually. And in this case, the quadratic variation process is not a deterministic process. Okay, very nice. So let us come to the stochastic integral now. And here we need a pre-visible process and an adapted process. The integrand and the integrator. The integrand, which is pre-visible, and the integrator, which is adapted. And then I can just define the stochastic integral using this formula here. And taking the integral, so that's something like a dx or so, because it's the increment the x makes in the step number s, and I'm multiplying this by h, which is pre-visible. And one basic thing here is that if x is a martingale, then h times x is also a martingale. Of course, I have to be a bit careful, because for x to be a martingale, I have to have that x is integrable. And if here, of course, all the random variables which are written here, they also have to be integrable at least. So let's just assume h is bounded or so, then that's not a problem. Let's compute that the stochastic integral h times x, so that's a funny notation for an integral, but I will do that consequently here, h times x. So why is that a martingale? I have to subtract the two things here. I'm just using the definition because I get the same thing as this here at time t. So ht minus 1 times xt plus 1 minus xt. ht plus 1 is ft measurable because ht is pre-visible, so I can put it out of the expectation here. And I end up having here this martingale difference, so conditional on ft, that's 0. And I'm done. Okay. Characterization of martingales. Here we saw that if x is a martingale, so is h times x. And here we have the other way around. It's also true that if h times x is a martingale for every pre-visible process h, then x is already a martingale. So the other direction also works. In particular, but that's just a small consequence, if x is a submartingale, h times x is also a submartingale. And again, I have here pre-visible. Okay. So let's prove number 1, and number 2 is just similar. So from left to right, we already had that. If x is a martingale, then the stochastic integral is also a martingale. So let's look at the other direction. In the other direction, I'm free to choose an h in order to conclude that x is a martingale. So I can, for example, have hs equals the indicator that S equals T for some T in my index set. So H is a process which is 0, and if I had T, I have 1. By assumption, I have that H times X is a martingale. But H times X, what is this actually? This H here in this example is 0 almost always, except for if S equals T, then I have a 1 here. So I have that the expectation of H times X by time T given Ft minus 1 must be 0, because I assume that this is a martingale. On the one hand. On the other hand, H times X at time T, well, at time T I have a 1 here. At time T I have 1 here, but before that I also always have zeros. So that's xt minus 1. So this here equals the expectation of xt minus 1 given ft minus 1, which now already shows that this martingale difference condition on ft minus 1 is 0. So that means x must be a martingale, because I can do that for all different t's that I have. Okay, so let's bring the things together. For example, we can now compute the quadratic variation of a stochastic integral. So first we learned about the quadratic variation, and now we learn about stochastic integrals. We learned that h times x is a martingale if x is a martingale and h is previsible. So we can now compute the quadratic variation process here. We had a formula for this. The formula for the quadratic variation process is, well, take the martingale at time s, take it at time s minus 1, square it, and compute this thing here. Okay, I have a difference here of two stochastic integrals at two time points, which means I just get one summand here, which is this one. hs times xs minus x minus 1. I square both of them. hs is fs minus 1 measurable, so also hs square is fs minus 1 measurable. So I can put it out of the conditional expectation here. And I have this here. And that means, for example, because we had this formula, where is it? Here. This here. So the expectation of the quadratic variation process equals the variance of the increment. It's here, the variance of the, so the expectation of the quadratic variation process is the expectation of this thing here. Well, what is this? Okay, if t equals 0, I have an empty sum here, which is 0. So the expectation on the one hand equals the variance of this stochastic process, the increment of this. It starts at 0, so that's just the variance of h times x by time t. And that's the same as the expectation of this here, which is written here. So by using this, I can compute the variance of the stochastic integral by time t, which is sometimes useful. So let's look at one thing how to view this. Already on the first slide I said, what is a previsible process? That's a process how much you bet in the next round. So let's say you trade a stock or something, and the stock price increases or decreases by this here. So the stock price by time s equals xs, and the stock price by time s minus 1 is xs minus 1. And at time s minus 1, you can bet about what happens in the next round. So you borrow some money and you bet on this. And then afterwards, you get a reward, which is exactly hs times xs minus 1 after this round, after you give back your borrowed money. So hs is something you bet on, so the amount of money you bet, and x is the increment which determines the payoff that you get. And interestingly, what we just showed in this picture, if x is a martingale, then also h times x is a martingale. So what does that mean? So h times x is this thing here, which is the amount of money that you have after time t when you bet hs in the round number s. And we just saw if x is a martingale, then h times x is a martingale. So you cannot really gain or lose anything by just betting on something which is a martingale. That's what it means. And there's a paradox on this, which is called the Petersburg paradox, because, for example, if x is plus minus 1, s is the corresponding martingale. And you get, let's say you get some, as you can bet some money on the occurrence of a 1 here. And since chances are half, your money is doubled when you bet on the right thing. So for example, if you bet plus 1 and it comes the plus 1. And in this case, it's very easy to come up with a strategy where you always win. And the strategy is as follows. Okay, you always bet on plus 1. If you bet €1 to start with, if plus 1 comes, you have gained something. Okay, that's good. If you have a minus 1, you have the next round, and you do not bet €1 in the next round, but you bet €2 in the next round. So you had €1 in the first round and €2 in the second round. If then in the second round you have a plus 1, the €2 that you just bet is doubled to €4. So you lost 2, you lost 3, and you gained 4. So in effect, you gained €1. And you can continue. If in the first 2 rounds you had 2 minus 1s, you must bet €4 in the third round, which is hopefully doubled, so you get €8. But you only bet it using 4 plus 2 plus 1 equals €7, so you always gain €1. And this strategy is this thing here. So if st minus 1 equals minus t minus 1, which means there were t minus 1 occurrences of a minus 1 previously, then you bet 2 to the power of t minus 1 euros on the occurrence of a 1 in the next round. And you can compute, as we just did, that ends up always having, in the long run, €1. So how can it be? Because we said that h times s here is a martingale if s is a martingale. And this martingale here starts with 0 and it almost surely ends up in 1. So that cannot really be a martingale, because martingales are known to have constant expectation, for example. So how does this work? And the point here is that you potentially need a very much money. So the amount of money that you need in order to get this €1 for sure, that has an expectation which I compute here, is infinity. So h, this process here, has not the right integrability condition. So we can compute this ht here, so the sum of all ht's. So in round number t, you're betting 2 to the power of t minus 1. Okay, I'm adding everything up here. So that's 2 to the power of k for something. Yes. Yeah. What am I doing here? -1, I don't know. So let's say that's 2 to the power of k, and that happens with a probability 1 over 2 to the power of k, because that requires that I have k times a -1 previously. So there's very small probability if k is large. With a very small probability, you have to bet using a very large amount of money. And when you add all this up, that's infinity, which means you will need, in expectation, infinitely much money in order to get this €1. So we really need some integrability conditions on h on all what we are doing. Okay, that was it for today from me, and hope to see you next time. Bye.